Hi, this is Dr. Liu. In this video, I'll introduce you the concept of momentum. So momentum is a concept that is very similar, if not confusing, with kinetic energy. So let's see what it is. We use P for momentum, and it is equal to mass m times velocity v. And as a comparison, kinetic energy is 1/2 mass m times velocity v squared. And sometimes I see students missing the square, so that makes kinetic energy almost the same as momentum, except for a 1/2. So what are these differences? And I'm pretty sure the similarities, they both involve mass and velocity, right? The differences are quite clear after this discussion. So first, let's take a look at the units. So units of momentum is kilogram, that's from the mass, meters per second, and units for the kinetic energy is joule, right? So that is what, let's say 1 joule. That's kilogram for the mass, meter squared per second squared, or sometimes we write it as 1 Newton. That's kilogram meter per second squared. We have an extra meter, right? So what this tells us is it hints us that in order to transfer energy, we need a force, we need to sustain that force with a displacement of a certain amount of distance, then we transfer energy in joules, right? Here, this side, we don't really have another name such as a joule to name this, so this is it. We can try and make this look like that, such as a Newton, right? Kilogram meter per second. If I multiply 1 more per second, I'll get a Newton. So this is kilogram meter per second squared, but times the second back, right? And that is equal to 1 Newton second. So this gives us a hint how to transfer momentum, how to increase, decrease momentum. You still need a force, yes. And instead of having the force displace an object, or at least the object is displaced, you have a time duration. You apply force for a duration of time, which is different from applying force for a distance. Although this distance implies time has to be spent, which means when you're transferring energy, you are also likely transferring momentum, vice versa, right? So it's a different type of transfer, is a different type of unit. Okay, so that's one difference. So they're not to be equated or compared in quantity. And another difference is momentum is a vector. So P, let's put this, P is a vector. So momentum in the direction, say to the right, is different from momentum to the left. That's because this momentum is equal to m times vector v, right? So the direction counts. You could have different momentum just by traveling in different direction, even with the same speed. On the other hand, kinetic energy is a scalar, because we have the square of velocity. So if you're traveling up, down, left, right, with the same exact speed, regardless of direction, your kinetic energy is the same. So that tells them apart further by saying that this is a vector here, this is a scalar here. So scalars are typically easier to handle. We handled vectors before, forces, right? They're not that easy to handle. We need to break vectors into components. We can only add components along the same axis or in the opposite direction. We cannot add components that are in orthogonal directions. Try to subtract and add their quantities, their numerical values would be invalid. So kinetic energy should be easier to handle because it's a scalar. You are supposed to add, subtract their numerical values. And momentum, on the other hand, is not. Okay, so here's just a quick comparison, and let's do some calculations of typical momentum like we did in typical kinetic energy, right? So we had a small ball fire a small ball and at the typical speed, say 5 meters per second, and we concluded that the kinetic energy was in the quantity of joules, right? So some joules or a fraction of a joule. So what about momentum? So a small ball. So small ball projected at 5 meters per second. So let's say mass equals small ball 0.01 kilograms. So 10 grams is a small plastic ball. Alright, so let's calculate momentum. This is just magnitude because the direction depends on which way the velocity is. Right, so this is 0.01 times 5, no need to square, 0.05 kilogram meter per second, or if you want 0.05 Newton second. This is telling us how to transfer momentum by applying force for duration. So it's a small fraction of a unit quantity in Newton second. What about a human being? Okay, so an average adult running, say at 5 meters per second. That's fast. And let's say average adult. Let's give 75. Oh, let's make it easy for ourselves. 80 kilograms, right? So momentum magnitude is mass times velocity is 80 times 5. So it's 400 Newton meter, or in this other unit, whichever you prefer. So 400 units of momentum. That is hundreds of units for a human being that's running. What about a vehicle? A car. Going at some highway speed, so let's say 30 meters per second. That is roughly 66 miles per hour. So let's put that in there. 66 miles per hour. And let's say mass is equal to 1200 kilograms. So vehicle. And the magnitude of momentum in Newton seconds is 1200 times 30. So 36,000 Newton meters, or 3.6 times 10 to the 4th Newton meters. And I remember calculating these for kinetic energy. The kinetic energy is in the hundreds of thousands of joules for a car moving about that speed, and the human being would be hundreds of joules of kinetic energy. So these quantities are similar because the speed of a human being is just a single digit meter per second. You cannot be very fast. If you're running 10 meters per second, that's very impressive. I don't know how long you can sustain that. So these are the quantities that we're looking at for some everyday items and human beings. And since we talked about momentum in this way, Newton times a meter, so I want to do a little bit of introduction of how momentum is transferred by forces. So here on the right side, basically the relation between forces and momentum. So we start with Newton's second law. This is something we have used for a while. All right. So either with or without calculus, we know that the average acceleration is a change of velocity over change in time. With calculus, you can write this as dv or dt, but it really doesn't matter in our case. So the change of momentum, the change of velocity or change in time. And then if we multiply this whole equation by delta t on both sides, then we have F delta t equals m delta v. All right, so let's assume that excuse me, m is a constant, just for simplicity. So m delta v, this means mass times the change of velocity is the same as delta mv. So the change of velocity times a scalar is the same as the change of mass velocity, because this mass does not change. The only thing that changes is the velocity. So it's like this is if this mass is 3 and the change of velocity is 5, then you can just say 3 times whatever velocity is, and then minus 3 times whatever previous velocity was. So this change can be, the mass can be factored in if the mass isn't changing. So then we realize the mass velocity is momentum, right? So the left side is force and time, so force, duration, and the right side is change of momentum, right? So now we know for sure that how to change momentum. It is to apply a force for a duration of time. And you can also say that F equals delta P over delta T. So this is the alternative format for Newton's second law. A force or net force changes momentum over time. And in calculus, we also do this dp or dt, but really doesn't matter in our case where we're able to use some average changes and such small changes, right? So this is how momentum is changing, is because you applied a force and for duration. So so this is going to get explained later in another video how to calculate change in momentum using this equation. I think this is pretty much enough for the for momentum. Just think about momentum as another quantity, although it's very similar and sometimes confusing with kinetic energy. It is a vector quantity and it has a different unit. It has a different way of being transferred, although they do sometimes transfer together with kinetic energy. In later videos, I'll explain how to make use of momentum in situations such as collisions and so on, so that we can find out, oh, actually momentum can be quite useful when kinetic energy is not able to help us getting our answers. Thank you.